Welcome to my third video covering Isaac Newton's text, The Method of Fluxions and Infinite Series. In the previous two videos, we've been talking about expanding variables out in terms of power series. In the first video, we were talking about quantities that look something like this. We had a squared plus x squared. We want to take the square root, but what we want to do is expand this out as a power series. So that's what we did in our first video. And in the second video, we covered what we now call Newton's method, which is a way of approximating roots to functions. For example, if we had, let's say, x squared equals 2, we could also rearrange this as x squared minus 2 equals 0. And we could apply Newton's method to this function, which I might call f of x. And we saw that we can develop a recursive relation, which will approximate the root to this equation. And what we're going to cover in this video is quite a large topic dealing with algebraic curves. Now, what an algebraic curve is, very simply put, we're going to have two variables, x and y, and an algebraic curve is just going to be some polynomial using the x's and y's. So it's going to be a polynomial in the x and y's. For example, we could have the following polynomial, x squared plus y squared minus 1. And to fit the definition of an algebraic curve, that polynomial has to be set equal to 0. So this is a pretty simple algebraic curve, and we could think of its plot very easily. Hopefully you recognize that the plot of this function here is going to be the unit circle. And of course, you can have different sorts of algebraic curves using degree 2. You can have different objects like circles, hyperbolas, ellipses, and parabolas too. But what we're going to consider are more exotic algebraic curves. For example, we might have an algebraic curve which looks like this: x cubed plus y cubed minus, let's say, 3xy equals 0. And it's not quite so obvious what this graph is going to look like. And it turns out that once you start going above degree 2, these curves get quite exotic in their shapes. And what we're going to do in this video is we're going to discover a method by which we can expand out y in terms of x. So what we're going to have, or what we're going to develop, is a method for finding a power series for y in terms of x, the independent variable x. Before we get started laying out Newton's method for doing such a thing, I should motivate why we care about something like this. And let's return to that graph for that equation for the circle, x squared plus y squared minus 1 equals 0. And to remind you, the plot is going to look like this. It's going to be that unit circle. Now, suppose I wanted to know what values of y are going to be on this graph when x equals, let's say, 0.5. That is to say, I'm interested in that point and that point right there. I want to know what those two y values are going to be. Now, what does this calculation entail? What I have to do is solve this equation for y. And that's not so difficult to do. Just solving for, let's say, y squared first. I can rearrange this as y squared equals 1 minus x squared. And then discover that y is equal to plus minus the square root of 1 minus x squared. So the difficulty in calculating y is merely the same difficulty as calculating the square root of 1 minus x squared to find what the y values of these 2 points would be. Now let's go to that other equation, x cubed plus y cubed minus 3xy equals 0. Now first of all, I have no clue what this graph is going to look like. Actually, I do. I could put this into Wolfram Alpha, but let's say I can't do that. So a priori, I have no clue what this graph looks like. And let's ask the same question. Let's ask at x equals 0.5 Actually, let's say x equals 1. We'll keep it simple. X equals 1. What are the y values of the points on this graph? Now, what does that calculation entail? I substitute x equals 1 into this equation. I get 1 plus y cubed minus 3y equals 0. And then I have to find what these y values are going to be. Now, I can do this. This is just solving a cubic equation. But solving a cubic is much more difficult than solving a quadratic. And let's further suppose that we had some other algebraic curve. Let's say it's even more exotic. Let's say x to the 6th power plus x to the 3rd power plus y cubed, I'm just making up terms here, plus 2, or let's say 3xy minus 7 equals 0. And now you can see that in this algebraic curve and in this algebraic curve, it's not so easy to solve for y. So the whole point of doing this sort of power series expansion is to calculate, using an infinite series, what the y value is going to be for some given x value. Now let me show you what Newton does to find such a power series for y in terms of x. And I pulled the following algebraic curve right from the text. We have y to the 5th minus b, where b is just some number. Okay, it could be b equals 1, b equals 2, whatever, but it's not one of our two variables x and y. Minus b y squared plus 9b x squared minus x cubed equals 0. And again, it's not so simple to find what y is going to be given some x value. For example, x equals 1/2 or x equals 1. Now here's what Newton does. He looks at the powers of x and y for each of the 4 terms here. Now this first term, we can think of this as x is 0, y to the 5th power. The second term is going to be x is 0, y squared. This term here is going to be x squared, y to 0. And the last term is going to be y cubed, y to 0. Just ignoring all these coefficients for now, just focusing on the x's and y's and their corresponding powers. And here's the major insight. What he does is he makes a graph, and on the horizontal axis, we're going to have the powers of y. So y powers there. And on the vertical axis, we have the x powers. And let me just make some grid lines here. We'll see what's going on in a second. 1, 2, 3, 4, 5. And on the vertical axis, I'm going to have 1, 2, and 3. And what he does is he plots these two powers as a coordinate on this grid here. For example, we have a term, this first term, which is y to the 5th, which we're going to think of as x is 0, y to the 5th, and we're going to plot it on this graph. So we're going to plot it right there. It's 5 powers in y and 0 powers in x. And now this term here is going to be plotted right there. 2 powers in y and 0 in x. Here we're going to plot it right there. 2 powers in x, 0 powers in y. And this term here, we have 3 powers in x and 0 powers in y. What we have now is we've converted this equation into a chart here. And now, here's another major insight. What Newton's going to do is he's going to look at this vertical axis first, and he's going to identify the lowest point on this axis. In this case, it's going to be that point. And what he's going to do, he's going to first imagine, or at least this is what I take him to be doing, he's going to imagine a vertical line being drawn through that first. And in the text he says, imagine a ruler. You put a ruler vertically down like that. And now what you're going to do is you're going to take this ruler and you're going to rotate it that way and that way. So you're going to rotate it counterclockwise. So you're going to start to rotate it around this point. You're going to hold that point right there. And you're going to start to rotate that ruler. So the ruler, when it's getting rotated, it's going to start to look like that. And what you're going to do is you're going to keep rotating it until you start to touch some of these other points that you have over here. And then once you've done that, you're going to stop. And it turns out when you do it like this, we rotate it like that, the line we get is going to connect this point and this point. So this ruler, metaphorically, this ruler is going to touch that point and that point. And now what you're going to do is you're going to focus on that point and this point, these 2 points touched by the ruler. And then you're going to go back to this initial equation, and you're going to set those 2 terms equal to 0. So let me now do that. So the 2 points touched by the ruler are that one and that one. This is the x squared term, 2 powers in x, 0 powers in y, so it's going to be that term right there. And this one's going to be 2 powers in y, no powers in x, so it's going to be that term. So what I'm going to do now is take those 2 terms, minus b y squared plus 9b x squared, and just set it equal to 0. And now I just simply solve for y. I get that by squared is equal to 9b x squared. And you'll see that upon solving for y, and also assuming that b is not equal to 0, that y is going to be plus minus 3x. Now what's this telling us? Before, we had no information about what this curve is going to look like. But now what we have is a first order approximation for what this curve is going to look like close to the origin. Now from inspection, we know that the point 0, 0 is going to be on this graph, no matter what value of b we have here. Just because if you substitute x equals 0, y equals 0, the left-hand side is going to be 0. But now what this approximation is suggesting to us is that near the origin, this curve has 2 branches. We have that initial point there, 0, 0, and let's plot the equation y equals 3x, positive 3x first. And then we also have that other line, y equals minus 3x. So it's telling us that close to the origin, this curve is going to look something like this. It kind of has this X-like formation there. But this is also very nice too, because in addition to knowing that the point 0, 0 is on this curve, what if we ask for x equals, let's say, 0.1? Let's say we draw the vertical line there at x equals 0.1. What the y values of these 2 points are going to be. And this approximation is telling us that y, let's say y1, because now we're going to have 2 solutions, y1 is going to be approximately 0.3, because we have 3 times x. And then y2 for that other line is going to be minus 0.3. So we have, in an approximate sense, the point 0.1, 0.3 is approximately on the curve. And correspondingly, the point 0.1 minus 0.3 is also approximately on the curve. And if you do a bit more calculation, just pick some value for b, you'll see that these are actually very good approximations for what's actually going on with this curve. And if you plug this equation in to Wolfram alpha, the one I tried out was when b, that constant, was equal to 1. What this curve actually looks like is something like this. It comes in from the lower left-hand corner, goes up to the origin, does a loop-de-loop around here, and it comes back down toward the lower right. And this is very nice because it sort of confirms our hypothesis. Well, actually, we know that the point 0, 0 is on this curve, but it confirms our hypothesis that around the origin, we get this branching sort of behavior here. It kind of looks like that X a little. You may be wondering, what if we want more accuracy to approximate these points a little bit better? We have this first order term here, but can we continue out with this power series? That is, what we have so far is that y is approximately equal to 3x, But can we continue on? Can we find another term, let's say plus, let's say a, where a is some unknown number, times x squared? Can we continue out this power series one more term so that we get this quadratic term, maybe we get a little bit more accuracy? And the answer is yes. And it turns out that we're going to use a very similar concept to what we did in Newton's method. Let's say we are interested in this this upper branch here. So that would correspond to this sort of location here on that curve. That would correspond to y is equal to 3x. What we're going to do now is modify that 3x. We're going to tack on some unknown number p. So now we have y equals 3x plus some unknown number p. And we're going to substitute this y back into the original equation. And what you're going to get is going to be a new polynomial. So this is going to be a polynomial in the variables x and p. And then what you're going to do is you're going to solve for p. And that's going to give you the quadratic term here. But to do this sort of calculation, I'd like to now transition to the example that Newton actually uses so that we can get a little bit more practice with the chart that Newton sets up here, and also this concept of finding the higher order terms in this infinite series. Here I've written the example that Newton works out quite extensively. It's going to be the curve y cubed plus a squared y, where this a is just some constant, minus 2a cubed plus axy minus x cubed is equal to 0. And now let's write out that chart that we used in the last example. So again, I'm going to make this chart. On the horizontal axis, I'm going to have the y powers that show up. And on the vertical axis, I'm going to have the x powers. I see here that in this equation, the highest y power is going to be the y cubed. So I'm going to write out this graph to the number 3. So I have 1, 2, 3 there. And the highest one for the x's is also going to be 3. So I have 1, 2, 3 there. So I've made my chart here. Now let's plot this first term here. This is 0 powers in x, but 3 powers in y. So that means I should plot this right there. Here I have no powers in x, but 1 in y. So I should plot that right there. Now here, this is 0 powers in x, but also 0 powers in y. So I should plot that at the origin. And this is one thing to point out when doing this chart method, is that these constant terms are going to be plotted at the origin. Here I have 1 power in x and 1 power in y. So I'm going to plot that right there, 0.11. And here I have 3 powers in x and no powers in y, so I'm going to plot it right there. And now I'm going to use that ruler sort of argument here. I'm going to first identify the lowest point on the vertical axis, which is this point right here. I'm going to place my ruler down vertically first, and I'm going to rotate that ruler counterclockwise around that point. So I'm going to rotate the ruler counterclockwise just until I start to touch some of these other points. So when I rotate it like this, my ruler is going to start to look like that. Rotate it a little more, and then I notice that I start to touch these other 2 points here. And I forgot to mention too that when you identify when you're going to stop rotating your ruler, you want to make sure that all of your other points on this graph, like that one and that one, are above and to the right of the ruler. And we see that that's correct here. And I notice here that the ruler touches 3 points. It touches that point there at the origin, touches that point there, and that point there. And now I look at those 3 points. I go back to the original equation. I have that point there, the 0, 0. That's going to correspond to that term there. I have the term corresponding to 1 power in y and no powers in x. That's going to be that term. And I have the one which is 3 powers in y, no powers in x, and it's that one there. And what I'm going to do, take those 3 terms, y cubed plus axy minus 2a cubed, and set that equal to 0. I neglect all of the other terms. And this is really the power of the method, that I'm neglecting more and more terms so that it becomes easier to solve for a variable. And by inspection here, and this is sort of the artificiality of the example here, Newton just constructs this example so that by inspection I notice that y is equal to a. And you can see that this is true. You get a cubed plus a cubed, that's 2a cubed, minus 2a cubed, and that's indeed equal to 0. This is sort of a constructed example here, but here you would need to solve for y exactly. So that's our first approximation for y. This is like our zero order approximation. But the information that I get from this is that on the curve of this equation, let me graph that out here, I know that the point 0, a is on the curve. So let me plot that right there. And that's really all the information I have at this point, that the point 0a is on the curve. And if you go back to this equation here, you'll see that the point 0a does create 0 on the left-hand side. Now, suppose x is not equal to 0. Suppose I want to know what points are like right there. Let's say this is like 0.1 or something. What this means is that y is not exactly equal to a for all values of x. So what I'm going to do now is use that concept that I was suggesting before. I'm going to modify this solution, this a. I'm going to turn it into a plus p for some unknown value p. And now what I'm going to do is I'm going to substitute that y back into the original equation. So I'm going to substitute a plus p into y. And what I'm going to get, let me just write this out, a plus p cubed plus a squared, a plus p, minus 2 a cubed plus ax a plus p minus x cubed equals 0. And now I won't bore you with doing all the distribution, all the simplification here. What you're going to end up getting is 4a squared p, when all the dust settles, plus 3ap squared plus p cubed plus a squared x plus axp minus x cubed equals 0. And the point here is that what we get out of this is a polynomial in terms of the unknown variables p and x. You can see that this is just a polynomial in terms of instead x and y, we now have x and p. Now what I'm going to do is apply the exact same procedure here that I was applying up here for x and y. Up here I was using x and y. Now I'm going to apply that method for x and p. On the vertical axis, I'm going to keep the x powers there. But now on the horizontal axis, I'm going to have the p powers. And when you go through this procedure, you're always going to keep the x powers on the vertical axis, and you're going to keep the other variable on the horizontal axis. And let's now make this graph here. I see that the highest power for p is going to be 3. So I have 1, 2, 3. For the x's, I see that the highest power is going to be 3. 1, 2, 3. And now let's make this graph. This first term here, I see that it's no powers in x, but 1 in p, so I'm going to plot it right there. Here I see that it's 2 powers in p only. This is 3 powers in p only. This is 1 power in x only. This is 1 power in x and p, so it's going to go right there. And this is 3 powers in x. And now I lay that ruler down vertically. I see that the lowest point on the vertical axis is that point right there, the first power in x. And now I start to rotate that ruler counterclockwise. So I'm going to rotate that ruler about this point. And then my ruler, I'm going to stop my ruler right there when it starts to touch that point. And I confirm that all the other points are above and to the right of that ruler. And now I observe which points the ruler touches. I have that point, which is first power in x only. That's going to be that one right there. And I have this other one, which is 1 power in p only, which is that one right there. I take those two terms, 4a squared p plus a squared x, and I set them equal to 0. Now up here I was solving for y, but now I'd like to solve for p. And let's do that. I get, first, let's suppose a is not equal to 0, so I'm going to cancel out those a squareds. I have 4p is equal to minus x, just shuffling that x onto the other side. I get p is equal to minus x over 4. Now this is pretty nice here. Up here we had the 0 order approximation. Here we have the first order approximation. We have x to the 1 power. And hopefully you can start to see that our power series for y in terms of x is going to be y is approximately equal to a. That's our first term that we obtained there. And now we have another term here that we just calculated. We now have a minus x over 4. So now we have two terms of our power series. Here I've just copied all the information we've just obtained. I have the original equation. I have that second polynomial that we have in terms of the x's and p's. And I have our approximation for p, which was minus x over 4. And I also have our developing power series for y in terms of x, which is now a minus x over 4. And I'd like to continue out this calculation one more term to get that quadratic term, just to show you that we are actually getting a power series here. And the technique is exactly the same. This p being minus x over 4 is really only an approximation for what p is. So what I'm going to do is tack on another unknown quantity. Let me call it q. So that p is now x minus x over 4 plus q. Now what I'm going to do is I'm going to substitute that value for p into this polynomial that we have for the x's and p's. So this is going to go into that polynomial up there. So substituting, I get 4a squared minus x over 4 plus q plus 3a minus x over 4 plus q squared plus minus x over 4 plus q cubed plus a squared x plus ax minus x over 4 plus q. And then I have minus x cubed, still equal to 0. And you can see here, what I now have is another polynomial, which is in the x's and q's now. And now I do some simplification, then I won't bore you with that. Let me just tell you what I get out of that. I get 4a squared q plus 3aq squared minus axq over 2 minus ax squared over 16 plus q cubed minus 3xq squared over 4 plus 3x squared q over 16. And last term, minus 65x cubed over 64 is equal to 0. And now I'm interested in finding what q is. And hopefully that q will be a quadratic term in x. And to do that, I apply the very same technique that I've been outlining. On the horizontal axis, I'm going to have the q powers. And on the vertical axis, I'm going to have those x powers. Remember, I want to always keep those x powers on the vertical axis. And for my chart, I see that the highest power for q is going to be 3. So I have 1, 2, 3. My highest power in x is also 3. 1, 2, 3. And now I make that chart. Here I have 1 power in q only. Here I have 2 powers in q. I have 1 power in each. I have 2 powers in x, 3 powers in q. I have 1 in x and 2 in q. I have 2 in x and 1 in q, so apply it there. Then finally I have 3 in x only. And again, I lay my ruler down vertically. I identify the lowest point on the vertical axis, which is that one right there. And I rotate my ruler counterclockwise. I start to rotate like so. And then you're going to hopefully see that I stop the ruler right there when it touches that point right there, which is first power in q. And I see that the other points over here are indeed above and to the right of my ruler. And I see that the 2 points touched by the ruler is going to be the second power in x only, which is that term right there. And the second one is the first power in q only, which is that term right there. And I neglect all of the other terms. So you can see how this technique is going to drastically simplify things. And I take those 2 terms, 4a squared q minus ax squared over 16, set that equal to 0. And now solve for q. I get that 4a squared q is equal to ax squared over 16. And upon solving for q, I see that it's going to be x squared over 64a. And that's it. Now what this means is that I've now obtained the quadratic term in this power series expansion. So now I add that to my approximation for y. So I have plus x squared over 64a. And hopefully you can see here that I'm building better and better accuracy for the behavior of this curve around the origin. The method for obtaining the other terms from here on out is just rinse and repeat. This is the term that we had as an approximation for q. And I had a polynomial in terms of x and q. And what you do to continue on is you attack on an additional factor, let's say r. You have q is equal to x squared over 64a plus r. Substitute that into the polynomial, which was in terms of x and q, and you get a new polynomial in terms of x and r. And then you solve that to obtain your cubic term. And I won't write out all the details of that, but if you do that, you'll find, and this is also written in the text, that the cubic term is 131 x cubed over 512 a squared. But you can see the power of this method is that all of the stuff that we've been doing, at least for the lower degree terms, it's just hand calculation. It's quite simple. But we can start to get an idea of what this curve is doing, at least around the origin. For example, let's take the special case where a is equal to 1. So the curve, the algebraic curve that I'm dealing with here is y cubed plus y minus 2 plus xy minus x cubed is equal to 0. And from the work that we've been doing, if a is equal to 1, then the power series expansion around the origin is going to be 1 minus x over 4 plus x squared over 64 plus 131 x cubed over 512, and that's it. And of course, there are other terms that are just waiting for you to calculate them, but this is the approximation around the origin. And of course, if you wanted to ask the question at x equals 0.1, let's say, what are the corresponding y values? Actually, you're only going to get 1 here, but you can see that an approximation for this would be that y is going to be approximately equal to 1 minus 0.1 over 4 plus 0.1 squared over 64 plus 131 times 0.1 cubed over 512. As with all of my videos, there's tons more to say about this topic. One thing we haven't discussed is the convergence of these series. For example, there might be some values of x for which this series does not converge. That's certainly an issue that needs to be fleshed out further. And I believe that the technical term for what we're doing here is the Puiseux series. We're finding the Puiseux series of the algebraic curve about the origin. At least I think that's what's going on here. And what's interesting about these sorts of series here is that the increments here, that is, we have x to the 0, x to the first, x squared, x to the third, and so on, that these increments need not be integers. And see if you can come up with a few examples yourself. But you might find that your power series, when you do this whole technique, may look something like this. You get x to the 1/2, then your next term is just x to the first, then you get x to the 3/2, and then x squared, x to the 5/2, and so on. You might find that these are the variable powers here. And by the way, if you look into this topic further, you may find that the technical term for that chart that we made for the powers of the two variables is called the Newton diagram, or Newton polygon. And the Newton polygon is a topic to talk about on its own, but it's continuing that ruler metaphor where you have your points and you start to trace out a polygon that sort of encloses those points. And it has a relation too to finding series expansions as well. But hopefully you've enjoyed this video. It's a sort of introduction to Puiseux series, algebraic curves, and doing some calculations with them. But it also exemplifies what Newton is trying to say here, is that we can have these very complicated looking expressions here, but using the technique of power series, using the technique of infinite series, we can take that dependent variable, let's say y, and we can start to think of that variable as a power series expansion in the independent variable, in this case x. So just another example of how this power series and infinite series technique is quite useful in many domains of math. And if you're following along the text, I forgot to tell you where we are in the text too. It's the ending part of the section called reduction of what Newton calls affected equations. And I presume what he means by affected equations is just an algebraic curve, but it's the part between what we were doing last video and up to what's called problem 1. And to give you a teaser for what's going on in the next video, problem 1 is where we're going to finally start to do some calculus. And what we're going to do is we're going to take the fluent quantities, let's say x, and we're going to find a way to calculate the fluxion of the fluent. If x is the fluent, then the fluxion is going to be x dot. We're going to start to talk about the x dots. We're going to talk about derivatives. So hopefully you join me for that video. And if you enjoyed this video or any of my others, feel free to subscribe to my channel, like the video, and stay tuned for more videos on Newton stuff. Thanks for watching.